to save. Oh, Maxwell wants to save the file into an Excel. So this is the command how we save a CSV file. Where's my chat? I lost my chat. Okay, here. Maxwell wants to save the new variables in the new data set into a new file. Okay, for example, oh, I need to have much bigger screen. What can I undo? Uh, uh, Wait, how can I lost my last one. How can I undo? Yeah, okay. Here, we created new variables in our example.a5. So I will type example.a5. This is our data frame. And then I call this a new example a2.csv. Can you see my command at the bottom? That's how I
Yes,
say.
but do we leave a vacant space between new and example, or we should add underline?
It doesn't matter. It
Okay.
doesn't matter for the file name, whether you want a space or underscore or full stop, doesn't matter. Okay. In fact, I don't want to show. Shouldn't be any bullet point. Okay, here. This is the command. This is the command. You save it as you save your new data frame, example.a5, as a CSV file, and then the file name is here. You can use whatever file name you want. You can just call it new.cs2 CSV. Okay, so you can have space or underscore within the quotation, which is the file name.
Okay. Thank you.
Okay, good. So now you know how to recode. Okay. In particular, we will do a lot of recoding using we will recode all those negatively worded items such that the items are in the same direction. Otherwise, your factor loadings will have some positive and some negative factor loadings. And also, we want to recode age and tenure, okay, if they are in years, okay, because the variance of that may be much larger than the variance of the other items. After you have recoded all this, you can save it in a new CSV file. Okay, if, for example, you save your data frame example.a5 into a new CSV file called new.csv. Of course, you can do all this on your Excel spreadsheet, but you can also use R to do this. Missing data. be very, very careful about missing data. For missing data, a lot of times when we conduct surveys, we have missing data. So in your Excel file, in your data file, the missing data should use a space or NA to represent. In the past, R required that to be NA, but a few years ago, they allowed to use space. For missing data, there are three types of missing data. Is missing completely at random, missing at random, or not missing at random. Missing completely at random is very good because some people miss out question 1, some people miss out question 5, some people miss out question 10, and it's totally random. If this is the case, it will not affect your estimation. It will not affect your estimation. Then the second type of missingness is missing at random. Missing at random means that the missingness is not due to the variable that you have the missing value. Let me first explain not missing at random. Then you will understand missing at random better. What is not missing at random? It is because of the answer of that question and they don't want to tell you. Therefore, they miss it. For example, when you ask somebody's income, if they are earning too much, then they don't want to tell you. They just skip that question. Or they're earning too little, so they don't want to tell you about this, and they will miss this question. So the missingness is due to the answer of that question. Then it is the most problematic missingness. We need to use some auxiliary variables to estimate the missingness. What that means is we need to include some other variables to predict a person's income such that we can predict whether it is what is the value of that missing value. It is most problematic, but a lot of cases, we hope that we don't have this. Missing at random is not because of that particular response, but because of some other variables. That happens most often in multi-wave data or longitudinal data. You will always notice that in wave 1, you have more respondents. Wave 2, you have fewer respondents. Wave 3, you have fewer respondents. They are missing because they are no longer in the organization. But it is not because of the answers. Therefore, it is missing at random. Although missing at random is not a very good term, people confuse it with the missing completely at random. Okay. Missing at random is also not a problem. Missing at random is not a problem in your estimation. If you have MCAR or MAR, it is not a problem in your analysis. Only when NMAR is problem. Unfortunately, there is no test for MAR. There is only a test for MCAR, missing completely at random. You can run the test either using SPSS, the missing value analysis. It's NITU's MCAR test to see whether it is significant or not, to tell whether it is missing completely at random. There's also an R package that I've provided a link here. Then you can test whether the missingness is completely at random. Even when it is missing, you fail the missing completely at random, there's still a chance that it is missing at random. So it's still not a problem. In management empirical studies, we seldom conduct this test. we seldom tell people whether you are missing completes at random or missing at random. Okay, unless the reviewer query whether you have the missingness which is missing, not missing at random. No matter which scenario, you cannot have missing percentage more than 10%. If you have missing percentage more than 10%, no matter what missingness you have, no matter what missingness you have, you will get a biased result. You will get a biased result. Okay. So in practice, okay, in practice, you may have 500 respondents in wave 1, 400 in wave 2, 300 in wave 3. Okay, so it is very, very typical. What you should do is to find out the to divide those 500 respondents in wave 1 into 2 groups. Those who have responded wave 3 and those who have not responded in wave 3. And then run a t-test or ANOVA on the key variables to see whether the variables are significantly different or not. It is to demonstrate that for those who have not responded in wave 3, their responses in wave 1 are actually not significantly different from those who have responded. Do you get my point? We just need to demonstrate that you don't have a biased sample. In the analysis, do not use 500. In a multi-wave analysis, if you have more than 10% of missingness, I will use the 300, okay, as the responses as for your analysis, not the 500, because you will have too many missing values in your wave 2, your mediator, and the dependent variable in wave 3. If I make myself clear? Hello? Okay, now, how can we handle the missing values? There are different methods. We can use listwise deletion. That means whoever have one missing value, you delete the whole case. It is not very realistic in empirical studies because we will encounter a lot of missing values. If you use listwise deletion, you may start with 500 subjects and you end up with 150 subjects. So listwise deletion, it is the default many, many years ago in Nashville, for example, but it is not advisable. Unfortunately, Laverne also used listwise deletion. Okay, I don't know why they don't change it. Okay, that means you will have a much smaller sample size. So don't use listwise deletion. Pairwise deletion, because XEM is based on the variance covariance matrix, or more or less like the correlation matrix. So it tried to calculate each covariance matrix with all those responses that have answered those 2 questions. This is pairwise deletion. Which is not a good idea because your sample size for each correlation coefficient or covariance coefficient will be different. R12 may have a sample size of 200. R23 may have a sample size of 250. So it doesn't know how to calculate, you won't know how to calculate the sample size. One other method is called mean imputation. Okay, for those missingness, we simply use the mean of all those who have responded to replace that missing value. Okay, there are 2 problems for mean imputation. It is not advised. Okay, I don't advise you to use mean imputation. The first problem is that you are creating data. Okay, that is most problematic. And second, you will notice that all those who have missing values in that item will get the same value. That means it will lower your variance of that variable. In other words, it will lower the statistical power of your analysis. So do not use mean imputation. Finally, regression imputation. It is simply using all the other variables to in a regression equation to predict your missing value. It is better than mean imputation because not everybody will have the same value. However, you are also creating new variable. You are also creating new data. Okay, so do not use these ad hoc approaches. Now, what are the new approaches that we use? Now the standard is called full information maximum likelihood. Full information maximum likelihood. Okay. Let me go back to a slide about the fit indices. Here. This is a slide I showed you about how SEM software estimate the parameters, and when it stops, it is an iterative process. It tries to minimize the delta estimate. It is trying to compare the sample covariance matrix and the fitted covariance matrix. But for FIML, full information maximum likelihood, it is not trying to create a fitted covariance matrix. It tries to create a new predicted data set and compare with the sample data set. Okay, so it is not comparing the fitted covariance matrix with the sample covariance matrix. It tries to create a new data set trying to compare with the sample data set. It only compare those data points which have values. So if it is missing, it will still be missing. It will leave it missing here. So the full information maximum likelihood method is now the standard. It is the default in M+. It is the default in M+ for FIML. There is another possibility, it's called multiple imputation. Multiple imputation is more or less just like regression imputation, but they change the regression coefficients a little bit for different trials. Multiple imputations means that you need to generate about 20 data sets. Each data set, you will use a different regression equations to replace the missing values. And you will run your analysis 20 times. And it will take the mean of all those estimates. That is multiple imputation. There's some researchers suggested that theirs also perform well, but I think now the standard is more using full information maximum likelihood. There are some statisticians, they create a new estimation method called expectation maximization, okay, which I don't understand very well. So what you need to do now in all papers, at the very beginning of your result section, you need to tell people how, or in your analysis section, you need to tell people how you handle the missing data. So first, you need to report how much missing data you have. Then you will say, we will estimate our model using full information maximum likelihood, okay, to handle the missing data. I have the two citations here if you want read the more about missingness and FIML. So all I would say is I would just put down full information maximum likelihood. In R, the missing data coded as NA or space. Because the default in R is listwise deletion, but we want to do it FIML. So in the SEM command, we will put missing equals to FIML. So I will ask for the full information maximum likelihood instead of using the default listwise deletion. Do you have any questions about missing values besides the question that Maxwell raised? No? Okay. Do we need to incorporate FIML in MeasureQ? MeasureQ already incorporates FIML. So when I wrote MeasureQ, it included FIML already. In fact, in all the programs that I wrote, like the one that I am going to show you on Monday, that I wrote with Professor Hu, Cheng Ya, the MEI measurement equivalence invariance, we also included the FIML already. Okay. So any questions about missing data before I go to your Maxwell's questions about power? Power refer to statistical power. What is the power of testing your hypothesis or finding significant results? Okay. Interestingly, last week I rejected a submission to ORM. Okay, I suggest to reject a submission to ORM, which developed a program to examine the power, statistical power of testing SEM model. The reason is it tries to estimate the power for mediating effects. Okay. What is power? Power is your probability of rejecting your null hypothesis when you should reject in the population. Or in other words, it is 1 minus type 2 error. 1 minus type 2 error. Type 2 error means that you should reject your null hypothesis. That means there are differences in the population, but you do not reject. What that means is, if you have significant results, we do not talk about power because you will not have any chance to make a type 2 error. If you already reject your hypothesis, if you already find significant results, then power is never an issue because by definition, you won't commit a type 2 error if you reject if you find significant results. Okay? Now, you will notice that it is very rare for people, it is not common for people to estimate power in SEM model. The reason is most of our SEM models have large samples. What I mean by large samples is, for example, 200. And you can imagine if you have a sample size of 200 in a regression analysis, actually most of the regression coefficients should have enough power to test a moderate effect size. Therefore, we typically do not estimate the power. People estimate power in two occasions. One, they say that we should estimate the power such that we know what sample size we need. If you have experience in collecting data, you will know that you don't have any control of the sample size that you get. So estimating the power is not meaningful. In the past, when we estimate the power, typically we estimate the power for t-test and ANOVA when we run experiments. When we run experiments, then we estimate the power. But when you run SEM, you do not estimate the power. Some people suggested that we should estimate the power afterwards. We should estimate the power afterwards if you do not have significant results to demonstrate that you have significant power, you have enough power, but you do not support your hypothesis. You do not get significant results. It is again very rare. The reason is, in order to estimate the power of each coefficient, you need to find out the effect size. You need to have an effect size, whether you want to test a small effect, medium effect, or a large effect. Then you can calculate the power. However, in SEM, there are no people who define what is a small effect, what is a medium effect, or what is a large effect. Therefore, there's no base for us to calculate the power. Some people calculate the power based on the sample estimates, which is stupid, because when we calculate the power, it should be based on the population parameters. Whether you want to test a small effect in the population, or a medium effect in the population, or a large effect in the population. If you use your sample estimates as your effect size, it is not meaningful. It is all about your standard errors. Okay, so I am somebody who do not, at least at this moment, I do not support estimation of power in SEM. So Jinfu has a question about if the exogenous variables have missing values, can FIML handle that? For the X variables, I'm not 100% sure. Okay. All I know is if you use LMS, if you have missing values in one of the components, then it will not calculate. Okay, but I think in exogenous variables, it should be fine. I don't know. Okay, I will give you the answer. If you ask me this question again next week, I can give you the answer. We use power analysis in effect size to determine the minimum sample size required for SEM. Really, I've just explained to you. The answer is yes, but it is not meaningful. Okay, even when you can calculate why this is not meaningful, 2 points. One, it is very difficult for us to define the effect size in SEM. Okay. Second, even when you have determined a minimum sample size to achieve adequate power for testing an effect size, if you have practical experience in collecting data, you have little control about the sample size. Do you get my point? Okay, so if you calculate a sample size, you will need a minimum sample size of 150. Okay, you go out to collect data. Okay, you will try, and anyway, okay, I would say a minimum sample size for SEM not a minimum sample size for the power. A minimum sample size for SEM is typically 200 or more, okay, to get a stable results. Even if you calculate, okay, a sample size, minimum sample size of 250, for example, it very much depends on your sample, how much you can get. Okay, you will try to get as much as possible, as many subjects as possible within your sample. You won't stop when you achieve 200, okay? You will try to get as many as possible. Nowadays, collecting data is different from the past. In the past, when we need people to send you the responses by mail, then you need to estimate the sample size. Now everything is online. This is not that difficult, especially if you use the online platform, for example, Prolific or mTurk, to collect data. Try to get a larger sample size, like 300 or 500, because it will not take you more time and you will have higher statistical power and easier to get significant results. Do you get my point? If you have control of the sample size, get as large as you can. If you don't have control, then estimating the sample size is not meaningful. Minimum sample size, I would still stay with 200. If you have lower than 200, for whatever non-significant results you get, I will question whether you have enough power. But it's not possible for you to demonstrate because you don't know how to define the effect size. Okay? Any questions? Now, Maxwell yesterday asked another question about correlation matrix. For published articles, okay, we will see them to publish a correlation matrix, the means and the standard deviations. Can we use this instead of the raw data to estimate an SCM model? Okay. Well, the answer is yes, but not very good. Okay. On slide 205, I shows you the syntax. First, you need to read, instead of reading a data frame, now you read the correlation and the standard deviation. Okay. Typically, when we enter a correlation, we use the lower triangle to input your correlation coefficient, your correlation matrix. So this is the correlation matrix. Then the next command, I should use smaller fonts so that you can read the commands better. Example A6. I'll pull out my example A6. My example A6 here. First, I enter the lower triangle. The next step is I need to convert this lower triangle into a data frame. So I would say get COV lower is this. And then I give names because we don't know what are the names, variable names in this matrix. I give names to these variables, the 7 columns. I also read the standard deviation because SEM analyze covariance matrix. So you need the standard deviation and the correlation matrix such that you can convert it into a covariance matrix. Again, when I input the standard deviation, we need to provide the names of the standard deviation. it is a vector, okay, and we need to give the names. The names. So there are two parts. First, you read the correlation matrix as a lower triangle, and then you give the names and read this into your data frame. Second, you define the standard deviation. You input the standard deviation like this, and you provide the names. Finally, you convert the correlation matrix and the standard deviation into a covariance matrix. So I have core to correlation to covariance. I have a correlation matrix and then the standard deviation. Xinhua asked a very good question, and Maxwell asked yesterday as well. The answer is no. Bootstrapping has to work on raw data. Bootstrapping has to work on raw data. It cannot work on correlation matrix and standard deviation. Okay? But I will tell you something interesting later. Again, you can define your model. Okay, this is the model that we had the first day. This is the model that we want to run on the first day. And then we have the syntax. We define the indirect effects and the total effects. Okay, and then we can run this model. Okay, now let's try to do this together. Okay, I am opening my outcode example A6, or if you want to refer to the slides, it is first you need to have slide 205, and then you need to have slide 207. So I got the results. Fit indices like this. RMSEA, SRMR, and then all the regression and R square. Have you got your results and the defined parameters? Yes. Now, both Maxwell and Xinhua asked a question about bootstrapping. Here, we want to find out what is the indirect effect, right? The indirect effect and maybe the total effect. And I also told you that indirect effect, you need to create confidence interval because A11 times B11 is not normally distributed. So you need to do bootstrapping. However, bootstrapping needs to draw new sample from your raw data. If you only get a correlation matrix and the standard deviation, it cannot do bootstrapping because there's no raw data for it to bootstrap. So a simple answer is that you cannot use bootstrapping to generate the confidence interval. But for those who were with me in previous years, you should realize that I wrote a program called MCCIMM, which creates the confidence interval based on the Monte Carlo simulation. Use the Monte Carlo simulation method. The Monte Carlo simulation method is based on the variance covariance matrix of all your estimated parameters, all the estimated coefficients here, the variance covariance matrix of these estimates. In that case, you do not need to have raw data. Okay, actually, you do not need to have raw data. What that means is you can use MCCIMM that we will talk about on Wednesday. On Wednesday, okay? Even when you have a correlation matrix as the input, you can still find the confidence interval, bias corrected confidence interval for the mediating effects and the total effects. Okay, have I answered your question, Xinhua? The answer is you cannot do bootstrapping, but we can do Monte Carlo simulation to find out what is the confidence interval for the indirect effect. But I am going to cover this on Wednesday. Well, okay. Now, why don't we take another break? We will have more break because we will have 4 hours today. Okay. You are not going to have lunch break. We will finish at 1. Why don't we take another 15 minutes break? Okay, we are going to take a 15 minutes break, and then I will come back to talk about two more models. One is the single indicator, one is the mean structure. Let's take a break now. Start at 11:35. Okay. See you in 15 minutes. Hey, are you back?
Yes,
Okay, can we start?
yes, please.
Okay, now before I move on, let me answer question. It's by Jin Fu. Jin Fu, are you here? Jin Fu? You're not back. So Jin Fu asked a question. Jin Fu asked a question whether FIML can handle exogenous variables. Okay, I've just tried during the break. That's why I'm 5 minutes late. Okay, so if you have missing values in the exogenous variables, FIML will remove the case. It will be listwise for um, um, exogenous variables. Okay, so that's the answer to your question. FIML can handle if the missingness is on the endogenous variables, not the exogenous variables. Now, I got another question by Eugene asking about the G star power software. Okay, again, she shows on the chat. Okay, I noticed that some people use that package, but you will notice that you have to specify the effect size as medium. Okay, how do you get what is a medium effect size? In SEM, okay, that medium effect size, whether it is 0.15, nobody knows. Okay, in particular, the problem is we do not have good effect size measures for mediating effects and moderated mediation. We don't have a definition of effect size for mediating effect and moderated mediation. Therefore, we can't estimate the power. So what Eugene has suggested here about the G star power, I know somebody uses it for SEM as well, but it is not correct. It is not designed for SEM. Okay, and again, it is not very useful. So I hope I have answered your question. Now, two more models before we go. One model is about the reliability corrected single indicator latent variable. Okay, I suggested that. Well, actually, I didn't suggest it, but I applied it in the latent interaction context. So how can we convert a single indicator into a latent variable? Again, this is the equation that we used yesterday. Here we have one known variable, which is the x. We have two unknown variable, lambda and the residual, eta. Factor loading and residual variance cannot be estimated at the same time. So in fact, what we will do is to fix the factor loading at 1, and the residual variance is fixed at 1 minus the reliability times the variance of x. Just like what we did yesterday. If the reliability complex alpha is 0.8, the variance of x is 1.2, then we define the residual variance of x, which is x slick 0.24 times x. So x slick x is the residual variance of x. We define the factor loading to 1. If you do not estimate the reliability, okay, then you need to put down, assume there's no measurement error, so you put down 0. As I mentioned yesterday, sometimes if you put down 0, you may have estimation problems. So I will put down a very small number like 0.001 here instead of 0. I just read an article, okay? Is that what I'm going to show you? Yeah, I'm going to show you next week an article that people mistakenly in setting the residual variance, they still use this, okay? 1 minus 0.8 times the variance of x. But for the factor loading, they didn't put 1 here. What they put is the square of the reliability, 0.8 times 0.8. So it is 0.64 here. So some people suggested that we should, instead of 1, we should put 0.64 here. How do you get 0.64? It is a square of your reliability. Okay? But this is wrong. This is wrong. Effectively, if you do this first line and the second line, you are assuming there's no measurement error. Effectively, you're removing the measurement error. Okay, so don't do this. Don't do this. This should be 1. It's not the square of the reliability. If you put the square of the reliability, you may come across some papers. They put down the square of the reliability. I can show you the equations later. If you put the square of the reliability here, then you will effectively turn the residual variance to 0. Okay, why do we need this? Do you remember in our previous example, we input the correlation matrix and the standard deviation to calculate all these parameters. However, in most of the journal articles, they also include the reliability, Comax alpha. So all those are not single items. They are submitted scales with Comax alpha. And they also report the standard deviation. So what we can do is to adjust, is to define the measurement error by using these 2 pieces of information. In our previous example, we do not have a measurement model because we assume that all these variables are measured without errors. However, it depends on the size of the reliability. You may get biased results of all these estimated parameters. Since they already reported the Comax alpha in the article, how we can make use of this is we first include a measurement model. All this measurement model create new latent variable L, supervisor's interpersonal justice, which is 1 times the supervisor interpersonal justice. And then we define the residual variance as 1 minus reliability times the standard deviation square. So it is 1 minus reliability times the variance. We convert all our observed variables into latent variables. So in this case, we will adjust for the measurement errors. And then we have our path model. Now we have our path model. And then we can estimate the model. So you may try to include page 215 and 216, or there is a file called, I have the file output example A7. Yeah, example.A7. Copy and paste here. Then you can see your results. So difficult for me to handle that many windows. Have you got your results?
Yes.
Yes, okay. I want to show you the results that we have before. This is the results that we have not adjusted for the measurement errors. But remember, the reliability of these variables are pretty high. If you look at your results, you will notice that instead of 0.267, I got 0.266. Instead of 0.260, I got 0.283. Do you know what I'm talking about? Here, for A22, instead of 0.394, I got 0.435. So you will notice that the estimates are different. Now the estimates are more accurate because we have accounted for the measurement errors measured by the complex alpha. Do you get it? Good.
Questions?
Yes.
Okay. So, if we follow this method, outstanding method, and we found that different outcome from those published, and then can we possibly write a conference paper to argue that hey, there is an issue if people just utilize the PAT model, or you have done that before?
Well, let's say no. Okay. I won't do this. Well, the answer is yes. You can tell people that if you are based on the path model, then you have made a mistake like this. No, because if you really do that, and if your paper get accepted, you are making another enemy.
Right.
You know what I'm talking about?
Definitely, yes. Outstanding
Okay.
advice.
Okay. So it's just for fun and for teaching purpose, and to remind people that if you use regression, you have measurement errors. And when you have measurement errors, actually your estimates are biased. Okay. So for the reliability corrected single indicator leading variable, the regression coefficients are more accurate. However, there is always a misunderstanding. When people compare between SEM and regression, they think that SEM has higher statistical power. The answer is no. It doesn't mean that SEM always have higher statistical power. Although your regression coefficients are more accurate, typically the regression coefficients are underestimated if you use regression that ignores measurement errors. However, when it calculates the standard errors, you will notice that the standard errors is a little bit larger. It's a bit larger than before. If I show you a 6, you still have your results. Do you notice that originally our estimate for A11 is 0.267 and the standard error is 0.088? But now when you adjust it for the measurement error, the estimate is 0.266, but the standard error is 0.108. 0.108. The reason why the standard error is larger because it incorporates the standard error that goes to this path and also the measurement error. So the standard error will include the measurement error as well. Here it assumes there's no measurement error. So typically the standard errors will be larger in SEM. because it incorporates the measurement errors. Okay, so we use this a lot, but not in this particular context. In the context where your model is very complicated, okay? In the past, when people develop scales, okay, the only criterion that they will use to evaluate the quality of the scale is complex alpha. And you know, there's a property of complex alpha is the larger the higher the number of items, even though the items may not be correlated, your complex alpha will be higher. Therefore, in the past, some researchers, when they develop their scales, they just want to have larger complex alpha. The way to do it is to add more items. So you will notice that some scales have 15 items, 20 items, okay? So I don't know why you really need 20 items to measure a construct. In fact, if you have 20 items in measuring a construct, there is a very high possibility that your SEM model will get rejected. The reason is those 20 items may have some items which are highly related to form a dimension. Therefore, the SEM model without the dimensions, the second order will reject your model with all those 20 items. A way to avoid this, to have too many items, my co-authors, I don't know why, a lot of my co-authors have small sample size. Maybe collecting data is really that difficult. They send me samples with like 120, 150 subjects. And they always ask me to analyze, to test very complicated models. And I say that you don't have enough sample size. You are testing more parameters than the sample size. So what we will do is, instead of estimating all the factor loadings, we take the simple average score and use the reliability corrected single indicator approach to adjust for the measurement error. I published a paper in 2021 in Journal of Business and Psychology, a simulation studies, showing that in the context of latent interaction, the reliability corrected single indicator approach, it provides you with very good approximation of the coefficients that you created, that you get from a full structural equations model. Okay, so it is very close approximation. In short, if you have a large enough sample size, if you can estimate your model, use the full structural equations model. If you do not have a large enough sample size, and you have many items, you have too many parameters to estimate, then you can take submitted scale, that means a simple average score across all items to represent each variable, and then use what we have just done here to turn the observed variable into a latent variable by defining the measurement error, Okay, so
And is there a citation we can utilize
yes,
this
it's
method?
2021 in Journal of Business and Psychology.
Okay, thank you.
Oh, okay. Finally, the final model that we will cover in this few days is a model with mean structure, This is a measurement model, the CFA. In fact, it has the intercepts and the latent means for the factors. relationship between an observed variable and the latent construct, xi. So your first item, x1, for example. Now, if we include a mean structure, which is regression, we use our factor to predict the observed score. We have an intercept, tau I, and a factor loading, lambda ij, plus the error term. This is the full equation that represents the relationship between a latent variable, latent factor fj, and an item xi. We can also calculate the covariance matrix. If we take expected value on both sides, that means the mean. Expected value of xi means the mean of xi. We still get tau I here. Here the delta, because it is random measurement error, this term becomes 0. Here we will have lambda ij times the mean of fj, which we use the symbol Kuiper, the letter Kuiper to represent it. So equation 3 shows the mean value. The mean factor mean is Kuiper j. It has a factor loading lambda ij, intercept tau j equals to the mean of the item xi. So this is the model with mean structure. When we estimate the factor loadings, we usually, because it is unidentified, we set a scale. We set the scale by fixing the factor loading of the first item to 1. In this particular equation, the mean of xi is long, but we have two unknowns here besides the lambda, the tau I and the Kuiper j. Tau I and Kuiper j. So the latent mean and the intercept, item intercept. What we will usually do is suggested by Bolen. Since the first item we fix the factor loading to 1, we also fix the tau to 0. We also fix the tau to 0. Okay? What that means is, if this is 0, this is 1, that means we define the mean of the factor equals to the mean of the first item. In fact, the mean, if you have only one sample, the latent mean is not very meaningful. You give me a mean of 3 versus a mean of 2 versus a mean of 0. It is not meaningful at all because we don't know unless we know what is your intercept and the slope. That's why in M+ in the Vern, in fact, in most of the SEM software, they do not define the latent mean. They set the latent mean to 0. Instead, they estimate the intercept of all items. So by default, in the Vern and M+, they estimate all item intercepts, but fix the latent mean to 0. In other words, it mean center all the latent variables. Mean center all the latent variables if you have only one group. Of course, you don't want to do that if you want to compare the means across groups. That is what we will cover on Monday. We will use a different method. So now we introduce two additional vectors, the intercepts and the latent means. These two vectors are not estimated from the variance covariance matrix. These two vectors are estimated from the observed means. It is not estimated from the standard deviation and the correlation matrix. These two vectors are estimated from the observed means. This is a latent mean of a 4-item model. We have x1 to x4. Rx1 means that the mean of item x1, mean of item x2, x3, x4. They all have tau 1 plus lambda 1 Kuiper. Okay, since we are talking about using 4 items to measure the same factor, therefore you only get one latent mean Kuiper. If we follow Boland, lambda 1 fix lambda 1 to 1 and tau 1 equals to 0, that means we effectively define the factor mean equals to bar x1. So if the mean of the first item is 3.2, then we will define the mean of your latent variable, factor 1 equals to 3.2. This is not meaningful. Okay, you may ask why we can use just the first item. If you use a different item as the first item, you get a different latent mean. Yes, that is the case. But the latent mean for one group is not meaningful. It is not meaningful in a single group because the intercept is set arbitrarily. Okay, so in a single group analysis, a simple average mean may be more meaningful. That means just take the average of the items. That will be more meaningful. That is what measure Q does. In your table 2, you see a column of mean, but in fact, it is unidentified in the measurement model. So we take the simple average of these 4 items. These are the different commands between Laverne and M+, but I will not talk about this today. We will come back to this next Thursday when we use M+. How can we estimate the mean? So this is the data file, and then we have the measurement model. All you need to do is to add this line that I have highlighted. Mean structure equals to true. And then I also add marker dot intercept dot 0 equals to true. What that means is we adopt Boland's identification method by fixing the intercept of the first item for each latent variable to 0. Okay? So now let's do that. Here's my result. You should notice that the 3 indices are exactly as before because we have used up all the known information here. Look at the intercept. Now you don't see x1 because x1 is the first item, therefore it doesn't estimate the intercept. You don't see x4, you don't see x7, x10, etc. However, you get the mean. You get the mean for your latent variables. You get the mean for your latent variables here. If you want to get the mean of your latent variables, again, it is not meaningful. I would prefer to take the simple average of the first 3 items to represent the mean of BE. The intercept is here. Now, I will do something which is slightly different. What if we do not set the default is the marker is false? That means we do not, what will happen if we do not set the intercept of the first item to 0? Now you get back this is the default in Laverne and M+. You get the intercept for the first item. You get the intercept for the first item. Okay? If you compare this with your period's results, do you notice that the mean of PE is 5.520? In the intercept for X1 is also 5.520. So in fact, 5.520 is the mean of X1. We use the mean of the first item, MS 4.116, so X4 you get 4.116. We are defining the latent mean if you only get a single group. We are not estimating the latent mean. We cannot estimate the latent mean, but we can estimate latent mean difference between groups. That's what we will do on Monday. Any questions? Maxwell, have I answered your question about latent means? Because you asked this 2 days ago.
Thank you.
For single group, it is not meaningful. Okay, I will suggest you, as I did in measure Q, to take the simple average of the items. Because if you use a different item as your first item, your mean will be different.
Yes. And can you clarify or explain the last two columns in this slide?
This slide,
Yes, the last two columns. Standard LB, standard O.
okay, I will not look at the intercept. Okay, I will not look at the standardized value of the intercept. But if you're talking about the factor loadings, let me show you this factor loadings.
Uh-huh.
Can you see my screen?
Yes.
Okay, so these are the factor loadings. Standardized all means that you standardize both the latent variable, that means you fixed the variance of latent variable to 1. You also standardize the observed variables. So you also standardize x1, x2, and x3. Okay, convert the items into standardized coefficients, and then you convert the latent variable to a standardized coefficient. Then you get standardized all. Standardized latent variable, you only standardize your latent variable, but you have not standardized your observed variable. Okay, so when we should use which? Typically, you should use standardized all. You should use standardized all as much as possible. However, if one of these items, x1, x2, x3, one item, for example, it is a dichotomous variable or it is gender. If it is a dichotomous variable, 0 and 1, you should not standardize this variable. You should not standardize this variable because it only has meaning at 0 and 1. It doesn't have any meaning when it is one standard deviation. Do you get my point? So if your item is a dichotomous variable, then you should use the standardized .lv. If these are not dichotomous variable, then you should use standardized all.
Thank you.
Good. So I have finished all the materials for today and for these 3 days. Now we still have time. Do you have any questions about introduction to SEM?
No, but can you clarify next Monday? Suppose there is no typhoon, and then we will meet in person. Okay. Yeah.
Okay. So if there's no typhoon, if we can go to class, it should be at National Taiwan University, the business school. I think we are going to meet at 9:30, right? Mingjie?
Yes, from 9:30.
From 9:30. 9:30. Okay. On Monday, I think I'm going to talk about measurement invariance and equivalence. So it is a big topic. Okay. And recently I wrote a paper with Professor Hu, Cheng Yang, and we developed a software that you can test the measurement invariance easily. So in the past, it may take you days to analyze the data. Now we are talking about minutes. Okay. On day 2, I'm going to talk about longitudinal data. There are 2 ways that you can analyze longitudinal data. One is the latent growth model. I will show you an example of latent growth modeling, a published article that I didn't show last year. So I will show you a published article where we analyze the data with latent growth modeling. And then I'm not going to talk about latent congruence model, but I will spend more time to talk about cross-lag panel model. So the second type of analysis that you can do with longitudinal data is a cross-lag panel model. Okay, I'm going to show you published articles and how we can reanalyze the data with a package that I developed. It's called CLPM. Okay, I will talk the difference between cross-lag panel model and random intercept cross-lag panel model, RICLPM. We'll have a software to test it. Again, it is very handy and it can save you a lot of time in analyze the data. And I can show you that in that published article, they didn't analyze the data properly. And I will show you how to do it. It's based on a published article. It's not any data that I created. So you can know how to use it when you test your empirical study. So it is new. On Wednesday, I'm going to cover moderation. That means latent interaction and moderated mediation again. But this year, I will introduce you to a new software which is based on R, which is called MODSEM. MODSEM. It's very newly developed. Okay. And I will talk more about this software. I didn't develop it. Okay. There was a genius. Okay. In fact, he's very young and he is not in academic. He's a statistician in Norway. Now I communicate with him every day. So there is a statistician in Norway. Okay, he developed a software package for his master thesis. It's only a master thesis. Okay, and developed a software package that we can analyze latent interactions. We can analyze latent interactions using our package. That's what I will cover on Wednesday. And of course, there's still a lot of limitations for that our package. Okay, I am forcing him to add more and more functions there. And also, I will show you how to link the MODSEM results with MCCIMM. So we will use the MODSEM to test moderation and moderated mediation. Okay. So I will tell you what are the advantages of using that software and what are the disadvantages. Okay. Finally, on Thursday, I'm going to talk about multi-level analysis again. Okay. For multi-level, we still need to work using M+. Now I'm working with that young fellow in Norway to see whether he can develop a software for multi-level random slope analysis using Laverne. Laverne can do multi-level, but it cannot do random slopes. So I'm forcing him, I gave him a paper to read, and hopefully he can work on it and develop a random slope model. Then in the future, we can get rid of M+. This is not my major objective, okay? But a lot of people don't want to pay M+ every year. So these are for next week. You have any questions? Okay, if not, I'll let you go earlier today. So we will meet on Monday. Okay, Mingjie has an announcement. Room has been moved to classroom 102 of the second building of the School of Management, the new building, okay? Closer to the MRT station. Oh, Mingjie, when we finish, I have something to talk to you, okay? So don't knock out, but the others can.
Okay.
Okay, so I hope you enjoy these few days. And I guess you need some time to digest. And I need some time to work on your homework assignment. Okay, I just worked out the second homework assignment. Okay, so wants to make sure that it's not too difficult. Okay, it's easy for those master students. Okay. So if you have any questions, you can still come to class and ask on Monday. On Monday, now you are finished with the introduction to SEM. On Monday through Thursday, we are going to cover some more advanced topics. Okay, but those are typically the topics that you will encounter when you work on your thesis or your empirical research. Okay, if you don't have any questions, I'll see you on Monday. Bye-bye.
Thank you, Gordon.
Well, one last question. Are we going to submit the exercise for grading or is just for exercise purpose?
We have about 10 students who register for this course.
Oh, I got it. Then I'm not. So thank you.
Yeah, you can work on the exercise, but you don't need to submit.
Okay. Thank you. Safe trip. See you next Monday. Thank you.
Yes.
Bye.
Yanchun, you have a question? You raise your hand. Jackson.
So, dear Professor,
Yes.
I would like to express my deep appreciation and thank you for your lesson. And I really
Right.
enjoy your lesson. It's very useful. And I just would like to ask because in next week I have the quickly scheduled working already. I cannot earth on Tuesday and Wednesday. So I asked wonder if we can have the hybrid mode to study online also because I really would like to study with you.
No, we don't have the online mode. I cannot do both online and in class at the same time. Sorry.
Mm.
Yeah.
I
Yeah,
got
I'll
it.
come every year to repeat the materials. Every year I have something new.
Yes, I got it. Thank you so much,
Okay.
Professor.
Sorry. So why people are not leaving? Mingjie, I want to talk to you only. We need to wait a little bit. At least you can be here, okay? But we need the others to sign out first. We're almost there. Okay, seems the others want to stay with us.